Okay, welcome to the second part of Chapter 16. When we left off Chapter 16, we were just getting to this section on encoder-decoder networks. And so we're going to cover those and talk about some advantages in this, including what's called attention networks. These are really cool because in the last 5 years, a lot of work has been done in these encoder-decoder networks and attention networks, particularly related to machine translation. So most of the efforts now, like to translate from English to French or French to English and things like that, are using these sorts of networks, and there's been actually a lot of advancement in recent years for that. The idea of an encoder-decoder network is to look at input and encode it in a certain way, and then decode it. The idea of an encoder, let me jump to this. The idea is to have a neural network that encodes it into some internal state, and usually this internal state will maybe extract some certain features and an internal representation of that, whatever the input is. In this case, it might be a sentence. And then the output, again, we train the network to decode this internal state to some output. And here we're often using, if you remember, in this chapter we were talking about recursive neural networks. So these could be recursive neural networks like long short-term memory networks, or these gated recurrent units here. And so we're often feeding like a word at a time into these units, and then we can feed an entire sentence into this, and it encodes it into some internal state, and then we can decode it out. Originally, these are actually trained with what are called auto-encoders, where you might encode it to create an internal state and then decode it to recreate the input. So you might provide a sentence in English, have it get into some very concise state, and have it generate that same sentence in English. Or if you replace this recursive neural network with a CNN or some sort of image processor, you might provide an input image here and have it generate the same input image, but in between encode that image into some smaller feature vector here internally. Now the book goes over this and talks about these encoder decoders. So again, providing an input sentence like I drink milk into here, and then we feed this through it and output like the French version of this as we go. And it talks a little bit about how this works and how it feeds forward, but they don't really have a great example of this. They talk about setting these up a little bit, but they really don't do any of this. Then they go and talk about bidirectional recurrent neural networks, and these are neural networks where the idea is that we often train these networks, if we feed it a couple words, to predict the next word. And so we'll be feeding in a sentence and train these in order to get a good internal representation, train these to predict the next word. But and sometimes we actually will provide the sentence in reverse order and have it predict the previous word. But bidirectional neural networks are set up so that they can take a sentence and fill in a gap in a sentence. So you could say, I like to drink blank from a cow, and the network should be able to fill in that blank word that's not there. And so it's looking both ahead and kind of behind at its inputs. And I'm not going to go into too much detail of how that works, but that's the idea. And we've seen some great examples of these bidirectional neural networks trained on. One of the things that's neat about these auto-encoding neural networks is that you can train them, like you can have them read the entire Wikipedia text, always just trying to predict random words that are missing or predict the next words. And so there's huge training sets available because you can have it train on English and predicting English for this. Now, a recent development has been this idea of attention mechanisms, and again, groundbreaking paper in 2014 was published, and a lot of work has been done since then. And the textbook tries to show this. So we have an encoder network that's taking this "I drink milk" sentence, and then you're feeding this into this alignment model, which then predicts which of these words are important to this output. And so as it's training, it'll see, well, when we're looking at lot, that correlates closely with milk, and so it'll tend to focus the attention or the representation on that. For this. Now, I don't love this version of explanation that the author has for this chapter. So I'm not going to use the chapter from this text. So instead, this notebook is going to come from a TensorFlow tutorial that's available that was put out late last year with the new TensorFlow 2.0. And it talks about neural networks and machine translation and attention. And again, Google's done a lot of the work on this sort of model. These are sometimes called sequence-to-sequence models because you feed it a sequence of words and it outputs a sequence of words for this. And so again, this one's going to be looking at translating from like English to Spanish and Spanish to English, back and forth. And again, what we're going to do is work with this attention model. And so if we see, what that'll do is try to look at a sentence like this: "Are you still at home?" and then the Spanish translation of that, and then try to find correlations between words in multiple sentences. Didn't mean to click on. Okay, so for like home and casa, those will be correlated. So if we see this, it creates this attention mechanism, and as it looks over all the words in that's training on, it finds comparison. So the brighter green, or yeah, the brighter some words are, the closer they are related at each other. So it'll like try to link up the relation that home and casa are related here, and show that, I guess, when you're seeing one word, where should your next attention be focused. So it builds up this sort of attention mechanism as it trains also. So you can actually go through this notebook and run it. Again, I'll have a link. This comes right from the TensorFlow documentation, and I really didn't change it at all. It works. It's a pretty nice notebook here. And again, they're bringing in a set of words, Spanish to English words, and it's downloading this, so this takes a little bit to download. And then we do some work with these. We have to convert them. Unicode is a generic and universal coding system for letters, but it makes some, it encodes thousands and thousands of different types of letters, where ASCII is an old style one, is just set up for like English letters, the letters you're used to, and so it's a smaller thing. So they do some conversion and processes the sentence here. So there's just some words here. They have a sample English and Spanish sentence here, and they show how they're going to process those. And then they tokenize these, and I think we talked about tokenizing last unit, where again each word is going to be assigned a number, and we're going to tokenize each word in our training corpus here. So they set up, and again there are methods here to tokenize things. Actually, I remember just a couple years ago we had to write all these tokenizers from scratch, and now they're all built in, so that's really handy. And then we're going to load in the data set here. And again, we're going to kind of limit this. We're going to not train it on everything. We're going to there are more than 100,000 sentences in this little training set, so we're just going to train it on 30,000 sentences to go through here. Okay, so yeah, here's how we do. We have this, and we also mark each sentence with the start and an end tag as we go. So we process these sentences, and we're tokenizing them. And so here's an example of a sentence, where is the car? And so we have a start and an end token, and then we have each word encoded as a number. So we're feeding it, 1, 71, 11. So this is the numbers we're feeding into this We're using a special structure in TensorFlow for our data set, and we haven't covered this too much. We've been using other structures, but this just puts the words in a special format so TensorFlow can train it a little faster and on multiple processors for this. And again, this is our kind of idea, is that we're feeding in a sentence here. The attention unit looks at the sentence and tries to figure out which areas, which nodes or words are important to the other words, and then we provide some translation of that sentence out of this for us. And so again, I'm not going to talk too much about this attention, but again, it's all based on this paper that was developed in 2014 for doing these. So and so then we have an encoder network, which is just a layer of a gated recurrent unit layer here. We do an embedding layer first, and then we feed it into this gated unit. And then we have we set up that network, and then we have the attention layer. And again, I'm not going to go into how this attention layer is set up too much, but that's just the idea. It's made with some of the units we've seen before, like the softmax units, and then some new layers to do a little bit of math in here. So it defines its own layers to do certain math features that it needs. So we have this attention layer set up, and then we have a decoder layer, and again, this is just these gated response units that are feeding in here. And then we put these all together into a hidden layer, an input layer, a gated layer, an input layer, a hidden, not hidden, I keep reading hidden here, an attention layer, and an output layer for this. So we have our encoder and then our decoder, and then in between that, kind of looking at both, is our attention layer for this. To get this to work with some language, they use a different loss function as far as predicting what things are doing, and this isn't absolutely necessary, but it does improve things. And so Google, I wouldn't necessarily put this in there, but Google does, because they like to do stuff like that just to optimize some of these. They also are going to save the network with this checkpoints. Again, we don't have to worry about that, but here we're going to do some training. And again, the way we have to train these networks are a little different, so it defines its own kind of training function, so we can't use its own training function. One thing we'll see is that with cutting edge networks like this, some of this you have to do a fair amount of proprietary coding. Like I say, you used to have to write coding for all the tokenizing, and then all that is built into the libraries in a following update. And I would guess this sort of training stuff will be built in to the next version of FIT, or within the next year. This would be all built into Keras and TensorFlow, and you wouldn't have to code this, because again, these are gaining popularity out there. And then we actually do the training, and again, we're looping through, and we're doing our own actual loop here. And again, this should be built into Keras in the near future for this. So we start training on these networks,